Okay. Well, in the previous video, we derived this weird thing called the Euler-Lagrange equation without really talking about some important details, like what exactly is that Lagrangian function that we've been focusing it around. We'll do that now, and we'll talk more about the context. Actually, this idea of taking an integral over a path and minimizing some quantity that's integrated over the path has a long history. This concept is called the least action principle, and you can find hints of it actually going back to the ancient Greeks. But in the 1600s and 1700s, there was much more discussion of it from famous mathematicians. There was also this French scientist named Maupertuis, who has an interesting history. There was, I think, a constellation named in his honor, but we don't use that constellation anymore. You can look up Tarendus, the reindeer, then Lagrange, and then, of course, there was William Rowan Hamilton, who is, I think, most strongly associated with this concept. It's often called Hamilton's principle, but sometimes you'll see it called Maupertuis' principle as well. So I've got the quote here from Marion's book, of all the possible paths along which a dynamical system may move from one point to another within a specified time interval, the actual path followed is that which minimizes the time interval of, now we can say it, the difference between the kinetic and potential energies. That's the definition of the Lagrangian. So yes, we can talk about that. Yeah, Hamilton was an interesting person too. What he wanted to be remembered for was this idea of quaternions, which was a generalization of imaginary numbers. I don't know if that's quite all that useful to physics these days, but he carved it on a bridge when he had the flash of genius, as this thing says here, in Dublin. Yes, so the Lagrangian, yes, we can now define it. The difference between the kinetic energy and the potential energy, K minus U. Actually, I think you could define it as U minus K, right? I think you can multiply this by a negative number and everything will be the same. The only difference, I guess, would be that the path integral is no longer minimized, but it's maximized. But, our derivation was agnostic to whether it was a minimum or a maximum. So that's okay. We know the kinetic energy depends only on the velocity, right? The x dot, the time derivative of the position vector. In general, the potential energy could depend on both position and velocity, but we're going to limit ourselves pretty much to gravity for the potential energy. And that's a conservative force field. We can list a bunch of properties of conservative forces, and one of them is that the potential energy is only a function of position, not velocity. So what can we do with it? It's interesting that you can take a conservative force, and that's, again, a force where you can derive the vector force as the gradient of a potential. And by convention, we use the minus gradient. Again, going down, flowing down the gradient rather than up. And we can now write out what the Euler-Lagrange equation looks like for this case, right? The Lagrangian is, let's use the standard definition, kinetic minus potential. So we know that it's a function, that the kinetic energy is just a function of, the magnitude of V, 1/2 mv squared, minus U. So now one of the terms on the left-hand side of the Euler-Lagrange equation is just the derivative of L with respect to position. So if the only dependence on position in L is in the potential energy, then it would just be the gradient of L. And that's what we mean by partial with respect to vector position. That's just the gradient. So because of the minus sign, it's minus gradient of U. We know that to be the force. So, all right, I've reproduced that up there. And now for the other side of the Euler-Lagrange equation, we have to take the derivative of L with respect to x dot, the velocity, and that's where the kinetic energy comes in. You can write it out in Cartesian coordinates, and then each component of the gradient, the derivative of the kinetic energy with respect to x dot, with respect to y dot and z dot. In this case, you can just do the derivative, you bring down the 2 and it's just m times x dot to the 1. And you can do that for all the components. So the overall vector the gradient with respect to velocity space, just like we had gradients with respect to momentum in the Vlasov equation, is just going to be a vector made up from those right-hand sides. That's just m times the vector x dot. Okay, well, the right-hand side of the Euler-Lagrange equation, we have to take the time derivative of what we just derived there. So now if the m is constant, this is just m times the second time derivative of position. And, you know, we sort of know what these things are, right? The left-hand side, the minus gradient of u is the force. The right-hand side is m times acceleration, F equals ma. We've actually derived Newton's second law, and, you know, Newton's first law is also a special case of the second law from this Euler-Lagrange equation, or Hamilton's principle of the minimization of the action. Yeah, so it seems like a lot of work to get back to Newton's laws, but as we will see, there are advantages to this type of Lagrangian dynamics. So first of all, rather than having to work with vectors all the time, when you're setting up the physics of a system, setting up the Lagrangian of a system, that's a scalar, which is in some ways a simpler thing to do. Yeah, so that's really all you have to do once you've set up the Lagrangian. Then everything else just comes by turning the crank of Euler-Lagrange equation. You don't need to worry a lot about the balance of the forces, at least from first principles. You can also do this in pretty much any kind of coordinate system you like. It doesn't even have to be a well-behaved orthogonal coordinate system, like, you know, Cartesian or cylindrical or spherical coordinates. You can basically choose any set of self-consistent coordinates that you want. You know, if you have n dimensions in your system, you need n coordinates, and if they're all sort of well-known functions of some other coordinate system like Cartesian, they will work just as well. You take the time derivatives of them, they're functions of the original coordinates and their time derivatives. You can write the Euler-Lagrange equations in those coordinates. Yeah, it pretty much can be any set of coordinates that you want. And these q's don't even have to have the units of length. You know, you could write the Euler-Lagrange equations in terms of angles, dl d theta, dl d phi, and we'll do that coming up in the next few videos. Yeah, so you can basically design the coordinate system that you want to make your problem easiest to solve. And if you've taken classical dynamics courses, you might have spent a few weeks doing that. Okay. Oh yeah, there's another interesting way of writing the Euler-Lagrange equations in that it's very sort of artistically symmetric. We can derive a generalized momentum that corresponds to any of those generalized coordinates just by saying that the momentum is defined as the derivative of the Lagrangian with respect to a given time derivative of that coordinate. Again, those coordinates don't have to have the units of length. And now, but if they did, right, if you go back to our standard Cartesian coordinates, we just did a couple of slides ago, work out that the momentum on the right-hand side there really is just the derivative of L with respect to x dot, right? That's the standard momentum. But if you define it this way, the Euler-Lagrange equation is just the time derivative of this thing that we defined up here as p, and on the other side, it's just the derivative with respect to the coordinate itself. So I just like the fact that these two equations are very similar, the definition of p and the Euler-Lagrange equation. It's sort of a pair where the only difference is where you put that dot. So I don't know, kind of elegant. So yeah, so we'll look at different examples of generalized coordinates. We'll look at, you know, either spherical or polar coordinates in a plane, so where that q can be a theta. And we'll also look at coordinates in the rotating frame for three-body problems, for the Roche-Loeb problem. Okay, yeah, so we will start applying these very soon.